basics that we represent signals as sinusoids, sine waves. So we looked at the mathematics of a sinusoid and we see that there are three things that we can vary: peak amplitude, frequency and phase. Today we'll look at how we combine multiple sine waves, like in this example where we have two different sine waves. If we add them together, then we get some resulting signal. And we'll start to analyse, okay, if we add multiple together, what shape signals do we get as a result? And eventually, hopefully today, we'll finish with showing the relationship between the signal and the requirements that us as IT professionals care about, which are things like data rate, how fast we can send bits, and characteristics like bandwidth and frequency. I want to show you some real signals, but it's not easy without specific dedicated hardware to capture a real communication signal that's been sent. You may have seen spectrum analyzers. Maybe if you were doing TC program, you would have some labs on. You plug in some cables and you can analyze a real signal. That is, you can view plots of a real signal, say from a Wi-Fi device, from a mobile phone, or from other transmitter. We do not have this hardware in this class, so we cannot do that easily. Maybe on your Android phone or your iPhone, you may have used some software to look at your Wi-Fi signal strength. This is Wi-Fi Analyzer. It gives you a plot of what it shows is the signal strength of different access points. So here's one access point. There are other access points around. You turn on your tablet and this program shows you the signal strength of different access points. And what it shows is, okay, the higher the value, the stronger the signal strength on this axis. And on this axis is different Wi-Fi channels or different frequencies. It's a plot of signal strength versus frequency. And another example, again a plot of, again in this case, real signal strength, and we'll see it's versus frequency. These three plots that I've shown you, this one, the Wi-Fi analyzer and the spectrum analyzer, all show a signal in the frequency domain. That is, peak signal strength versus frequency. This is not time here, it's frequency. So we need to introduce this concept of frequency domain. Currently we've just spoke about time domain, where you have the signal strength against time. Since we don't have real signals that we can analyse in class, the best example I can give is audio. So this is a recording of our lecture yesterday. In fact, it was a CS lecture yesterday. So audio is just another signal. Okay, when we talk, you're receiving signals. This is the recording of the audio loaded up in some audio editor application, Audacity in this case. So from time 0 through to time 1 hour 15 minutes. This is a signal plotted against time. So this is what we see with our sine wave. It's going up and down. Well, this is a real this is a real audio signal. We can zoom in to see, because it's over a scale of 1 hour, there are many different components. We can zoom in and keep zooming in, maybe highlight some part and zoom in on that. Still zooming. That's a very close view of the signal. You see, okay, it's something that's going up and down at what looks like random positions. But that's an example of a signal, in this case an audio signal, not something that's transmitted across a computer link. And it's zoomed in to the point, okay, this is 38.14 seconds, this is 38.145 seconds, so this is a period of 5 milliseconds here. So we'll look at some signals. In fact, in this class, the demos I'll use are some audio signals, but the same shape as any data communication signal. It's just so I use audio signals because they're easy to show in class. This is a signal in the time domain. We want to look at also the signal in the frequency domain. Let's explain what that means, the frequency domain. We have this general equation, or this equation, example equation that we had last lecture yesterday, where we have two components. The resulting signal is made up of the addition of two components. And I'll just repeat what we did yesterday. S1 of t is 4 on pi sine, what do we have? 200 pi t. And S2 of t is 4 on pi times by 1/3 sine 600 pi t. And let's write it over here so you will not forget it. The general equation for our sinusoid, S of t, is peak amplitude sine 2 pi ft plus the phase phi. So of our two components, we know the peak amplitude. Of component 1, it's 4 on pi, and a component 2, it's 4 on pi divided by 3. So it's just the multiplier at the front of the sine. We know the phase is 0 in these two cases, in this example. There's no plus component here. And we can find the frequency. Frequency 1 is from yesterday. The frequency of component 1, anyone? Someone? Was 100 hertz, because general equation 2 pi ft, we have 200 pi t, f must be 100. And of component 2, we got 300 hertz. And the signal on the screen is just a summation of those two. We note that there's some connection between the two component frequencies. F2 is in fact 3 times F1. If this is the case, if a signal is made up of sinusoid components where the components' frequencies are all integer multiples of 1, then that 1 is called the fundamental frequency. F subscript f, the frequency, the fundamental frequency. This is 1 times 100. This is 3 times 100. Therefore, the fundamental frequency of this signal is 100. Which is the frequency of this signal. That is, S of t, the one plotted, has a frequency of 100 hertz. This plot, and it's not so clear in your printouts, the top one shows S1 of t, the second one S2 of t, and the bottom one is the summation, that is S of t. The difference is, in the example we're using a specific value of f of 100 hertz. The plots use the value, we do not use a specific value of f, they use, as we see here, sine 2 pi ft, 2 pi 3 ft, so they do not substitute f for some specific value. But the shapes are identical. If you got your computer and plotted this, it would look like the top one. It's just the scale is slightly different. And similar, if you plotted S of t, you'd get something that looked the same as the bottom one. Just the scale here differs. We add the two sine waves together, we get this other signal. The frequency of this signal is 100 hertz. It's the same as the top one. The period is the same. You can see graphically the period from here to here, 1t, 1 period, is the same in both the S1 and the resulting S. By adding sinusoids together with varying those different characteristics, the amplitude, frequency and phase, we can create any communication signal that we want, that we desire. When people design communication signals, they often look from the frequency perspective. They care about the frequencies of the components. Rather than looking from the time domain, where we see the signal strength against the time, they may look at it from the frequency domain, which is the peak signal strength versus frequency. Here's our same signal, but plotted in the frequency domain. Where did this come from? Let's show how we plot in the frequency domain first. In the frequency domain, here we have the frequency, and on this axis, the peak amplitude. This is an uppercase F versus the frequency. In the time domain, it's the amplitude versus time. Now it's peak amplitude versus frequency. So what we do, if we look at our example, we plot for each component the frequency of that component and the peak amplitude. So we're plotting our signal S of t in the frequency domain. There are two components. Component 1 has frequency 100 Hertz. Component 1 has frequency 100 Hertz. It has a peak amplitude of 4 over pi. 4 over pi sine 2 pi 100 t. So what we do is we plot an impulse at 100 Hertz with a peak amplitude, or with an amplitude of 4 over pi, which is about 1.3. Our signal has, in fact, two components. The second component has a frequency of 300 Hertz, and the peak amplitude is 1/3 of 4 over pi. So we plot an impulse at 300 Hertz, and the height is 1/3 of the first one, which is 4 over pi 1/3. So this is just how we come up with this plot. Simply look at the components and look at their frequencies, the peak amplitudes, and in this case plot impulses at those frequencies. This plot, which is almost identical to the one on the screen, except it's got, instead of 100, it's 1 times f, where if you replace f with 100 you get exactly the same. This is the plot of our signal in the frequency domain. The one on the bottom here is the plot of our signal in the time domain. Same signal, just different viewpoints of it, looking at it from a different viewpoint. Why do we want to do that? Why do we want to convert from one domain to another? Because looking at it from the frequency domain is usually much more convenient for the needs of the people who need to design and analyse signals. And we'll show an example briefly. So that's the basics. A signal in the frequency domain, we look at the frequency components and their peak amplitudes. I think someone asked me a question yesterday. If they have, I give you in a quiz or an exam this equation at the top, and I ask you to plot that signal. Can you come up with this plot in the exam? Not very accurately, at least. You could use your calculator and calculate for different values of t and try and plot, but it wouldn't be very accurate. It wouldn't be very good in the exam. It's not easy. Similar, just by looking at these two, it's not easy to come up, oh, this is the answer, this is the summation of the two. In the exam, if I give you the same signal equation, can you plot this? Yes, you can, because you identify from the signal equation the frequency components of 100 and 300, the peak amplitudes, and simply plot the two impulses. So dealing in the frequency domain is generally, for the things that we want to look at in terms of signals, is often quite easy. Yep.
On the graph,
This is uppercase S. This is the peak amplitude, okay, the highest point. This point, that's the peak. Time domain, it's the amplitude, which of course goes up and down. Frequency domain is the peak for that component, the highest point. So we often show this as an uppercase S, meaning the peak amplitude, the highest point. Unfortunately, not all signals are as simple as two sine waves added together. This is an example of another signal in the frequency domain. It's not impulses, it's a continuous signal, just as an example. So they don't have to be just impulses, that can be more complex. In fact, in the time domain, this is a plot of a square wave, at least from 0 to some point, and then goes at one level and then to 0 for the rest of time. So just another example of a signal but plotted in the frequency domain. Let's look at another example, which is our lecture, or the lecture from yesterday, the audio. We have the plot in the time domain. I'll zoom back out. All right, that's across the 1 hour or so of our audio signal in the time domain. With this audio software, I can analyze that signal and find a plot in the frequency domain. It's called the spectrum, or the frequency spectrum. So this software has some tools that will do analysis and find the plot in the frequency domain. It's not perfect analysis, it applies some algorithms. It didn't let me do it. Why not? Oh, it only calculates across a short period of time. Otherwise it takes too long. It's coming. Okay, there it is. This is the frequency domain plot. Now, along the bottom we see the frequencies starting from 0 Hertz. This is 1000 Hertz, 3000 up to 20,000 Hertz. And on this axis we see this peak signal strength. It's just the scale used here is in decibels. We haven't explained decibels and we're not going to do it right now, but the thing to remember is that this decibels in this case is a logarithmic scale. So there's a peak. If I move my cursor, it highlights the peak. That is the highest point here. At 600 Hertz, 610 Hertz. So of the 1 hour or the lecture yesterday of me talking and other noise, the strongest signal strength was at the frequency of 610 Hertz. And then there are some other peaks. We see the next one, this small one down here, this one here is at 1321 Hertz. So the strongest signal was around 600 Hertz, and it gets weaker for the higher frequencies. Most of the signal strength is concentrated in this area. Okay? As you see, it gets weaker and weaker down to 0. Because this is a logarithmic scale, the way to interpret it is that every line, horizontal line here, represents a halving of the signal strength. What that means is the top one, if the signal strength is 1, then if this is 1, this is a half, this is a quarter, this is 1.0, 1.125, and so on, 1/8, 1/16. So down here is maybe 1/64 of up here. That is, it's very weak compared to the strong signal. Down here is very, very, very weak. So most of the signal is concentrated in this area. from 0 hertz up to what, 2000 and maybe up to here 3000, 4000 hertz. When people talk, the frequencies they generate usually range from 0 up to 4000 hertz. And that's demonstrated here, that from my lecture over that period of time, most of the components were from 0 up to 3000, 4000 hertz. There may be other background noise from air conditioners, from people doing something on the desk and so on, with higher frequencies, but they were very weak from what was recorded. The signal strength is much lower. So that's a plot of a real signal, but in the frequency domain. And at the top we have it in the same signal in the time domain. Now, some terminology that we care about when we deal with signals, when we want to design signals. One thing we care about is designing a signal which gives us a high data rate. Okay? That's what we want to get to. How can we send bits fast? Well, some of the things that define or characterize a signal is made up of, we think, sinusoids, different components, each with different frequencies. The set of frequencies in a signal is called the spectrum. The spectrum of our example signal, S of t, it included the frequency 100 and 300 hertz, so both of those values. In my audio from before, the spectrum was in the plot. This is a plot of the spectrum. The audio contains frequencies in all this range. That's the first terminology. The absolute bandwidth of a signal is the width of the spectrum. Simply the highest component minus the lowest component. The absolute bandwidth, sometimes just called the bandwidth, is the width of the spectrum. So in this example, it's 300 minus 100, 200 hertz. So we say the absolute bandwidth of our example signal, S of t, is 200 hertz. In our example audio, the absolute bandwidth is about, wherever it goes up to, about 20,000 hertz, because it goes from 0 up to 20,000. So we have spectrum of a signal, absolute bandwidth of a signal. In practice, we see that in this example, the signal strength is strongest here. Down here is very, very weak. There's small components, but very, very weak signal up to 20,000 hertz. Maybe there's even some out here. In practice, we define some cutoff, and we get what's called the effective bandwidth. And we say that, okay, if the signal strength is below some level, we will ignore that. In this case, let's say if the signal strength is below minus 57 dB, this line, we will ignore that. Or maybe 54, this line. That is, say all these values are 0. Then we would say the bandwidth of the audio ranges from 0 up to this point, which is about 4,000 hertz. In theory, we have an absolute bandwidth, which is the width of the spectrum. In practice, we talk about just the bandwidth, or the effective bandwidth, which is defined by different ways, but normally there's a cutoff and say that the components which are very, very small, we ignore, and we do not consider them part of the bandwidth. And we get what's called the effective bandwidth, or just the bandwidth. For today, we'll focus just on the absolute bandwidth. When we talk about specific technologies, we'll talk about just the bandwidth. DC component we'll see in a moment. The main point is that the data rate, the speed at which we can send bits, depends upon these characteristics of our signal. The bandwidth of the signal, or the absolute bandwidth of the signal, and the frequency of the signal will impact upon our data rate. What we want to do is go through some examples to show that. Calculate the data rate for some different signals and see the relationship between bandwidth, frequency and data rate. What have we got? I'm going to do some examples on the screen to show the summation of multiple sine waves to get what we've seen here, to get this. Here we added 2 sine waves together and got this shape. We can add more components together. We could add 3 components and get a different shape. And some examples of the output are shown here. Sorry, here. This is with 2 components. This is with 3 components with some pattern of how we add those components together. This is with 4 components. And this is with an infinite number of components. In theory, if we keep adding sinusoids in a particular pattern, we get a digital or a square waveform. What we're going to do is go through some examples which look at, okay, what if we use a different number of components? How does it impact upon bandwidth, frequency and data rate? We want to maximise data rate, and we'll see normally we want to minimise bandwidth. We'll talk about why shortly, or as we go through the examples. And as the person who designs or chooses the signal to be transmitted, they normally want to choose a signal which can be used to accurately represent the data. If I want to send the bits 1010, that's the data, I could use this signal on the bottom here. What I could say is, okay, if I want to transmit bit 1, I transmit high, and bit 0 low, high, low. The receiver would receive a signal, they'd measure. If it's high, it means I've received a bit 1. If it's low, it means I've received a bit 0. We could also use the signal above it to transmit the same sequence, because also it's got this pattern of high, low, high, low. In fact, we could use any of these to represent the same sequence of bits. The communications designer needs to choose the best signal which meets their requirements, which will be data rate, will depend upon data rate, bandwidth, and one thing that we cannot calculate but we'll talk about is accuracy of the signal. We'll come to as we go through the example. Let's clear this off and calculate the data rate that some signals can transfer or generate. In the example we just went through, I used the equation and we had a frequency of 100 Hertz. I'm going to go through an example and demonstrate on the computer. We'll use a frequency of 1000 Hertz. The first equation, or the first signal that we'll try, let's call it signal A. Same structure as before, but with a frequency of 1000 Hertz, so we get 2000 pi t plus 1/3 sine 6000 pi t. That's the signal, first signal we're going to use as an example. We can put 4 over pi out the front, but for simplicity I'll remove that. Why did someone put 4 over pi out the front? Where does that come from? Remember, the amplitude just changes the height of this. The reason these examples include 4 over pi is so that the height comes to about 1 here. And you see 1 at the top and on the subsequent ones. If we didn't have this 4 over pi, it would be slightly lower. That's all. Just to make the example look a bit nicer on the plot. It's not needed in our example. Here's our first signal. What's the frequency of the first component? Okay, these are the things you'll answer in the quiz. What's the frequency of first component in this signal? 1,000 seconds, hertz, 1,000 hertz. Because of the general form of 2 pi ft. 2,000 pi t, this would be 1,000 hertz of this component, and the second component, 3,000 hertz. What's the fundamental frequency of our signal? The fundamental frequency of this signal SA. 1,000, because two components are both multiples of 1,000. 1 times 1,000, 3 times 1,000, we say the fundamental frequency of A is 1,000. I'll simply write it as FA. That's also the frequency of signal A. What's the period of signal A? Of signal A, what's the period? If the frequency is 1,000 hertz, the period is 1,000, 1 louder, 1 over 1,000. Can you calculate the answer? 1 divided by 1,000. The period is the inverse of the frequency. Okay. Frequency 1,000 hertz, 1 divided by 1,000 seconds. So 1 divided by 1,000 seconds is 1 millisecond. So we know for our signal A, we know its frequency and period. What's its bandwidth? What's the bandwidth of our signal? The absolute bandwidth in this case. 2,000. Where do you get 2,000 from? The maximum frequency component minus the minimum. We have just two components from 1,000 up to 3,000. The width is 2,000. In a moment, we'll calculate the data rate that we can achieve. Let's first plot those signals. We'll close this one. And I'm going to use this audio editor to show these example signals. The signal A is made up of the addition of two sine waves. I can use some audio software to generate a sine wave. And on my computer, the software is called SOX. It's a software, or it's a sound editor. So it's called SOX. What it does is normally it converts one format of audio, let's say WAV file, to MP3 and things like audio processing. But it can generate files. Because we have no input, I say there's null input, and I'm going to generate an example called IT1000 hertz and a WAV file. WAV is just a format of an audio file, and in fact it stores the raw audio, it doesn't compress it. I want to generate a file called IT1000 Hertz, and I want to generate some audio. So I use a synthesizer, and I want to synthesize for a duration of 1 second. I just want to create 1 second of audio. So that's the one. And that audio, because it's going to be created, is going to be a simple sine wave. Okay? That's what we want to generate, a sine wave with a frequency of 1000 hertz. So you don't have to know how this works. It's just software to generate audio or to do audio processing. And now, hopefully, we have a file that contains audio which is simply a sine wave at 1000 hertz for 1 second. And to view that, I'll open in this graphical user interface, Audacity. Wrong one. Somewhere, IT1000. Okay, there it is. But of course, that doesn't show us much detail. We need to zoom in to see what it really looks like. There's the generated sine wave, which is just audio. If you play it, it will just be a constant tone for 1 second. We see, if we highlight one portion of it, from 0.002 to 003 seconds. That is, this is a period of 1 millisecond. From 2 milliseconds to 3 milliseconds is a period of 1 millisecond, and we see there's one cycle of our sine wave. i.e., we see the period of 1 second. If you count how many cycles over this, we see a period of 1 millisecond. If you count how many cycles through this entire plot, you'll see there are 1000 cycles of our sine wave. It's got a frequency of 1000 hertz. Let's generate the second one, which has the same but a frequency of 3000 hertz, because that's going to be our second component. And open it up. Again, we need to zoom in. The 1000 hertz sine wave and the 3000 hertz sine wave. We see it repeats 3 times per 1 millisecond. That gives it the 3000 hertz frequency. And now I want to combine them, because our equation, our signal, is the addition of those two. With one small exception, the second component should have an amplitude 1/3 of the first component. In these plots, the amplitudes are the same. So what I want to do is mix the two audio files, and at the same time reducing the amplitude of the second one. And SOX can do that for me as well. It allows us to mix audio. If I remember how to do it. We want to combine two files together, mix them together, and when we want to change or specify the amplitude with the audio, we talk about, or we can talk about the volume. So the first component is going to have a volume of 1. That is the 1000 hertz component. And we take the file, what's the file called? IT1000. And the second component is going to have a volume of 1/3, 0.333. And the file. It's going to combine those two files and produce one output file. Let's call it IT2. And now we'll open that one in our editor. Again, we need to zoom in. We see our signal A. That is a plot of signal A. Okay? The same as we saw in the slides, except that we've just generated this one. We see the period is the same as signal 1, component 1. So we still have our period of 1 millisecond, our frequency of 1000 hertz. Let's close the first two and just concentrate on the generated one and look at the spectrum. So currently we have the plot in the time domain. Here's the plot in the frequency domain. Now, because it applies some algorithm to calculate this, it's not always 100% accurate, but we see the two peaks. At 1000 hertz, there's a peak, and at 3000 hertz, there's a peak. The two components. And, okay, we have some peak amplitude, and the second component has a lower peak amplitude. It should be 1/3. So that this should be 1/3 of this one. But note we have a logarithmic scale here. That's why it doesn't look like 1/3. But if you do the calculation, you find with a logarithmic scale, if this is an amplitude of 1, this would be 1/3 because it's in decibels or logarithms. So that's our signal, SA. Now, what's the data rate that we can achieve with this signal? How fast can we send bits? How fast can we send bits with this signal? And the assumption we'll make is the high component we'll use to represent 1 bit, a bit 1, and when it's low, another bit, a bit 0. So how many bits per second could we send if we follow that rule with this signal? How many bits per second? Because that's what we care about as IT people. How fast can we send our data? In the highlighted area, we have one high value, or it's high for some point of time, from some period of time, and then it's low for some period of time. We could say that that represents 2 bits, a bit 1 and a bit 0. So if we transmit the high signal, it's as if we're transmitting a bit 1, and we transmit for some time the low signal, a bit 0. 2 bits there in the highlighted area. What's the time frame? Well, we see from the software, it's from 0.002 up to 0.003 in seconds, which is one millisecond, okay? Which is our period, okay? That's the time at which our signal or the cycle lasts. In 1 period, we can send 2 bits, or in 1 millisecond, we can send 2 bits. How many bits per second? 2000 bits per second. In 1 millisecond, 2 bits. In 1000 milliseconds, 2000 bits, or 2000 bits per second. So our data rate that we can achieve with this signal is 2000 bits per second. That's what, if you cannot see that, 2000 bits per second, 2 kilobits per second. What we're going to do is to look at different signals and look at their characteristics in terms of frequency, bandwidth, and data rate, and see how they compare. Let's look at a second signal, SB. And let's have the same shape signal, but try a different frequency. Let's write it and see what the frequency is. Here's another signal. We'll plot it, or actually we won't plot it, but here's another signal. What's the frequency of that signal, SB? Calculate the frequency of the signal. SB is sine 4,000 pi t plus 1/3 sine 12,000 pi t. Very similar to the first SA signal, except instead of 2,000, 6,000, here's 4,000, 12,000 in terms of the multipliers for the frequency. So the frequency is 2,000 hertz. First component, remember, 2 pi ft, therefore f is 2,000. 2 pi ft, f must be 6,000. Therefore, we have a frequency of 2,000, 3 times 2,000. The overall frequency of our signal, therefore, or the fundamental frequency, is 2,000, because both components are integer multiples of 2,000. Period. Calculate the period. 2 ms, wrong. What's the period? If you know the frequency, you calculate the period as the inverse of the frequency. Everyone has a calculator or a phone, they can calculate that if they can't do it in their heads. 50, half a millisecond. What's 1 divided by 2? Half. The period is half a millisecond in this case. With a higher frequency, we would have more repetitions, so the duration of one repetition would be smaller. Let's plot the... I'm not going to plot it in the time domain. It's the same shape as this one. If we plot it, it's the same shape except it's got a higher frequency. But it would have these two humps as it going up and down. In the frequency domain, we could plot it. 2 components at frequency 2,000. If this is 1,000, 2,000. At frequency 2,000, there's an impulse that goes up to the 1. The multiplier at the front is 1. 1 sine 4,000 pi t. And the second component is at frequency 6,000. 1, 2, 3, 4, 5, 6. And the height is 1/3 of the first one. Just remember, in the plot in the software, we don't have this linear scale, it's a logarithmic scale. That's why it's a bit different in the software spectrum. That's the plot of our signal B in the frequency domain. What's the bandwidth? 4,000. And the bandwidth is very easy to see from this plot. just look at the highest component and the lowest and the difference. It's the width of the frequency band. 6,000 minus 2,000, we get a bandwidth of our signal B of 4,000 hertz. What's the data rate we can achieve with signal B? Again, same approach. In every period, we have a high level and then a low level. In every period, we can send 2 bits. So how many bits can we send in 1 second? We can send 2 bits in 1 period. Although it's not this signal, it looks the same. In 1 period, that is the highlighted area, we have a high level and a low level, each representing a bit, so we could transmit 2 bits in 1 period. 1 period is half a millisecond. Therefore, we can transmit how many bits? 500, 1,000, 2,000, anyone else? 4,000 bits per second. Two bits in half a millisecond. 4 bits in 1 millisecond. 1,000 milliseconds in a second, therefore 4,000 bits in 1 second. Check, make sure you can follow those steps of working out the frequency, period, bandwidth and data rate. While you're checking that, I'm just going to open some other files. Actually, I'll generate the new file. So now we have 2,000 and 6,000. And we combine the two together. So I just took 2 sine waves of each. First one was 2,000 hertz frequency and the second one 6,000 hertz, and I added them together and I got this IT3 file. If we open that, then let's compare the two. And we'll zoom in a moment once everyone's clear on this. You know how to calculate the data rate? When we have signal C, can you come up on the board and calculate the data rate for me? Maybe not. Why not?
Is it always then 2 bits in 1 period of time?
In this simple analysis that we're doing, just to demonstrate what's happening, we're assuming we send 2 bits in 1 period, yes. In real life, it's not always that case. Okay?
But when we calculate, we use
In this case, yes, we're using 2 bits in 1 period because we're saying, okay, when our signal is high for some duration, that corresponds to 1 bit, a bit 1, and when it's low, it corresponds to a bit 0, for example. It doesn't have to be that scheme. But in this case, yes, it is.
How about the other case?
In the other cases, we will see them in 1 or 2 weeks. That is, there is a whole different other set of schemes that we can go through, and yes, it would change, but we'll see the relationship still hold. What we're trying to see is the relationship between the signal, the frequency, bandwidth and data rate, and see how they compare with each other. Any other problems before we look at the signals? You can calculate, okay? A bit. Which bit can you not calculate? We need to remember the basics of the components, find their frequencies, fundamental frequency. If they're all multiples of one frequency, that one is the fundamental. Period inverse of frequency, bandwidth, difference between the minimum and maximum component. Data rate depends on how many bits per period we can send. 2 bits per period in our assumption. Zoom in. The top one is signal A, the bottom one is signal B. Same shape. It's the same shape, except of course we see signal B has twice the frequency of signal A. That's the only difference in the time domain. In other words, for signal A, we can transmit 2 bits. In the same time with signal B, we could transmit 4 bits. So in this period, high, low, here, high, low, high, low. So, oh, sorry, I've missed a part. And compare the characteristics. Signal A, data rate 2,000 bits per second. Signal B, data rate 4,000 bits per second. Frequency 1,000, frequency 2,000, bandwidth 2,000, bandwidth 4,000. The main point to get when we compare A against B is that increasing the bandwidth increases the data rate. We want to maximize the data rate. That's one of our goals. If we want to increase the data rate, we need to increase the bandwidth if we use the same structure signal. Okay? We'll show later in another lecture, but the problem with bandwidth is that we only have a limited amount. We want to minimize the bandwidth that we use. So in practice, I want to minimize the bandwidth, but maximize the data rate. But this is showing us that to increase the data rate, we need to increase the bandwidth. Think increasing bandwidth increases your cost. Higher data rate, higher bandwidth, but higher cost. That's the disadvantage here. Let's try another signal, signal C. And in signal C, we'll add a third component. Signal C. Let's start the same as signal A. Sine 2,000 pi t, 1/3 sine 6,000 pi t. But let's add another component. And let's make it 1/5 sine 10,000 pi t. A new signal, a third signal, and let's do the same analysis and see what values we get. Same as A, except a third component, a third sinusoid is added. Same as A, therefore these components have the same frequency, 1,000 hertz. The second component, 3,000 hertz. The third component, 5,000 hertz. Do you see some pattern there? Do you see the pattern in their signals that I'm creating? 1, 1/3, or 3, 1/5, 5. The reason for this is to create this structure, which we'll see shortly. The more we add using this pattern will eventually lead to a square wave. Frequency of signal C is, so find the frequency, period, bandwidth, and data rate. Let's see the frequency for signal C. Anyone have the frequency for signal C? Why 1,000? Because each component is a multiple of 1,000. 5 times 1,000, 3 times 1,000, 1 times 1,000. They're all integer multiples of 1,000. Therefore, the frequency of the overall signal is simply 1,000. Therefore, the period is just the inverse of the frequency. Turns out it's the same as signal A. 1 millisecond, 1 divided by 1,000, 0.001 seconds. Bandwidth, 4,000. Now we range from 1,000 all the way up to 5,000 hertz. The width from the minimum to the maximum is 4,000. Data rate. What's the data rate for signal C? The data rate is going to be the same as signal A. In signal A, we have a period of 1 millisecond. We're assuming we can send 2 bits in 1 period. In signal C, we have a period of 1 millisecond, same assumption, 2 bits in 1 period, therefore the same data rate. So now we have 3 signals and we know the characteristics of the data rate, bandwidth, frequency. Let me plot the last one. I've calculated before with 3 components. Again, we need to zoom in. And I'll play the signal. It might blow up my computer. Let's see. Okay, exciting. That's just the audio signal. The three signals, signal A, B and C, are shown on the screen. And we have the data or the characteristics of each of those signals. Let's try and summarise what's the difference. So someone who needs to design a communication signal needs to choose the signal that meets their requirements best. So in this case, we have a choice of 3. Of course, in reality, there's other approaches. But if we can choose from these 3, which one's better? Which one do you want, A, B or C? Anyone? Three signals, A, B and C. Which one is better? B. B. Why is B better? Why did you choose it? B has the highest data rate, 4,000 bits per second. A and C, 2,000 bits per second. Normally we care about high data rate, okay? We want higher data rate. So, always use B. Well, no, there's some other trade-offs to consider. The other thing, A has a bandwidth of 2,000 hertz, B has a bandwidth of 4,000 hertz. The higher the bandwidth, normally the higher the cost of the device and using that spectrum. Because the range of frequencies we have available to transmit is limited. Therefore, the more you use, the less other people can use. And therefore, there's competition to get access to the bandwidth, and essentially, in most cases, you need to pay a license to use a particular set of frequencies. And the more you want to use, the higher it costs. So, B is better for data rate, but it's worse in terms of bandwidth. We want to minimise bandwidth, but maximise data rate. So there's the trade-off between A and B. Minimise bandwidth, maximise data rate. So we need to choose which one's better for us. Do I want high data rate or do I want low bandwidth? That's A versus B. What about C? Why would we use C? It has a low data rate and a high bandwidth. That doesn't meet our requirements. Why would we use C? I've said we want to maximise data rate, minimise bandwidth. C doesn't do either of them. It gives us the lowest data rate, same as A, and the highest bandwidth, same as B. Is there any advantage of signal C? We don't have it in numbers, but look at the plots. And I'll add one more plot there. Signals A and B had 2 components. Signal C had 3 components, 3 sinusoids. I've got another one which has 100 components. Same characteristics, but 100 components. Unfortunately, I need to zoom in again. "100 components, 3, and the top 2 are just 2 components. The more components, the closer we get to this digital waveform, and the more accurate our signal will be. Why? Because when we transmit it, if there are some errors, if what we receive is not exactly what we transmit, it goes up and down because of interference, then it's more likely that we will be able to fix those errors or detect the correct data if we have a more accurate signal. That is, in the top signal, it's possible if we transmit the top signal that because of some interference, what's received is that it goes low and then it goes low again because of interference. And the receiver would interpret that as 2 low signals, low, low, low. So the more accurate or the closer we are to this digital square waveform, when we transmit, the less chance of errors in the transmission. We don't have much more time to explain that. But let's summarise at least on the trade-offs. Higher bandwidth, higher data rate with the same signal. A signal with more components gives a more accurate signal, less errors. We don't have numbers for that. But of course, increasing the components increases the bandwidth. Increasing from 2 to 3 doubled our bandwidth. So, 3 things now. Maximise data rate, minimise bandwidth, minimise errors, or select a signal which is more accurate. And that's why there's no one solution. You need to consider your requirements and choose a signal which meets your requirements. Do you care more about bandwidth and data rate, or more about errors or accuracy? That's up to the designer. Can we try and capture how an error occurs? Of course, we haven't talked about this yet, but let's say we transmit the top signal. Looks something like this, which represents a bit 1 and a bit 0. So we transmit that. But when we transmit through a communication system, there is interference and there's noise from other sources. Same as when I talk to you, when other people are talking, it makes it harder for you to receive what I'm saying. So maybe what is received looks like this. Let's try and... It doesn't look exactly what it was transmitted. Maybe what is received looks like this because there's some other effects on the transmission. What the receiver does is looks, okay, in this time period, is it high on average? Yes. High, therefore it's a bit 1. Is it low on average? Yes. Therefore it's a bit 0. Therefore no errors. But what if we got this instead? What was received was even worse. That's what was received. Then it would, the receiver, okay, on average, is it high here or low? Okay, there's some low parts, some high parts. It turns out it's low on average in this period, bit 0. Here, it's low on average, that's below the level, bit 0. That would represent a bit error in our transmission. That is more likely to happen if the transmitted signal is not always high. In this case, this transmitted signal is always high. Even with some errors or some interference, it's less likely to bring the signal down below the cutoff. It's more likely for the higher one. So it's more likely to, there are more likely to be bit errors with this signal than with this signal. And therefore this one's better in terms of errors. But we will cover errors and so on in the next topic on transmission media. Let's finish. Just to recap on what we've covered. These diagrams here are what I've shown on the computer, but just with some different values. I used some specific values for our case. We went through this example, except I didn't use 4 megahertz. I had a bandwidth of 2 kilohertz. I just used different values, but that's the example we went through. And we showed these trade-offs. We need to choose between bandwidth, data rate, and accuracy. We want to minimize bandwidth because the greater the bandwidth, the greater the cost. Therefore, we want to minimize the bandwidth. We want to maximize the data rate. If we increase the bandwidth, we get higher data rate, but of course, we get increased cost. And we want to maximize the accuracy or minimize errors. And that's to do with the shape of the signal. And again, we have a trade-off between those three factors. Just checking what we've missed. Nothing. Let's finish there. What we'll do next week is just recap and talk a little bit more about this impact of errors and so on, and then talk more about digital and analog data.